Electric charges and fields. Electric charge is a fundamental property of some elementary particles, such as protons and electrons, right, which you know. And like charges repel each other, and opposite charges attract. So that really is the most we could say about it, right? That it's a property that some particles tend to have, and even if we say like kind of fundamental particles, so even like a proton would really not be fundamental. We could say there's things that make that up, like quarks, but those, right, we can say, well, they seem to have this property, and that's something that leads to to forces and behavior in a certain way. The SI unit is the coulomb. The charge of a single proton would be, I just write it as plus E, because really the electron is the thing that we might look at as having this fundamental charge. But it turns out that both of them are exactly the same in magnitude, just opposite in what the charge is. So this plus E or whatever, which is what we tend to use when we do electricity, we seem to go with the idea of a positive E charge. So that's 1.6 times 10 to the negative 19 coulombs. That's not an exact number, but it's pretty accurate. And then the charge on electron is just the negative of that. Another wonderful conservation law here: charge can be transferred from one object to another, but the total charge of a system, particularly a closed system, remains constant. Right? So you've got a certain amount of charges. They can jump from one atom to the next or whatever, but the total has to remain the same. You may remember some of this from grade 9. You remember maybe even did some labs where you rubbed some fur on some glass or something like that. And although you may do experiments like this all the time, if you ever walk across a carpet with some socks on or something like that and then touch a door handle. Right? So there was really two ways we looked at charging objects. The first, kind of really straightforward, right? Direct contact, or charging by friction. So you take, and you can see this little electrostatic series over here. I just sort of copied this from the textbook. So if you rub two objects together, basically different objects have a different strength, if you will, or different ability to hold on to their electrons. Right? So if you've got two objects here, maybe you've got some wool here, and then you've got a little sheet of aluminum, right? And you rub the wool all over the aluminum, right? What happens? And you can look at this here, and you can see, right, these things have different strengths, or if you look kind of more on a molecular or atomic level, you can see that in this case the aluminum has a stronger hold on its electrons, and so some of the electrons would jump, right, from the wool onto the aluminum. Right? Still the same amount of total charge, but more of them end up there. As a result, the aluminum ends up negatively charged, the wool ends up positively charged. Right? And then you can touch it yourself or whatever and get a little shock or something. The other way to charge objects is induction. So if you and the idea of this is without direct contact. That's really the difference here, that you could charge something without actually having to rub these two things together and let the electrons just jump from one to the other. So you got to be a little bit clever about something like that. So here's a little picture of how you might charge something by induction. The thing we're trying to charge here would be this sphere that we have here. We want to charge it. So what do? Well, first we just bring a negatively charged rod really close to it. So you can imagine this sphere starts out, as anyone would, equal number of positive and negative charges on it. But what happens when you bring the negative rod to it, or close to it, while the opposites attract, so more of the positive charges sort of line up there, if you will. It's just a way to think of it. The main thing, we know it's mainly electrons, but they sort of move away from it, so that as they move over to the other side. right? So then what you do is you bring a grounding wire near it, right? So you bring a wire here, you give these negative charges, which are over on the far side, a chance to escape. And just because they repel each other and want to get away from each other when they're all close, if you put this little grounding wire here, they will go down the wire and into the earth where they can spread out more and not be all clustered together as like charges. Then you move the rod away. So you get rid of that rod, and you can see that kind of in this final picture here. But now you've gotten rid of some of the electrons, and so what you're left with is a net positive charge on this sphere. And so that's induction, right? You don't actually touch, right? You don't actually let this ebonite rod touch the thing that you're charging. So we say that you induced a charge. All right, here's a question taken right from grade 9 science when we last studied this. After running with a hoodie on and taking it off, a person's hair stands straight up. Why is this? There's really two things happening here. First is, so when the hoodie's up, right, and you can go, I don't ever like remember much of this electrostatic series. So I would go up and look at something like this and say, well, if I really wanted to be specific, not that you really need to be here, but I would say, okay, well, here's hair. And what's the other thing we're looking for here? Let's assume it's cotton, right? So that says, well, the cotton has a stronger hold on its electrons. So that means electrons were transferred from the hair to the hoodie. Right? So while running, right. So while running, and it doesn't really matter like which direction. What matters is both of these things are charged, right? So both hoodie and hair have a net charge. Right. It's just the hair happens to be positively charged, the hoodie negatively charged, but that's not, like I said, really the most important part of this, just that they both have charge. Then you take the hoodie off, right? Now you're left with hair that has a charge, right? That has a net charge. Right? So as soon as we take this hoodie off, you've got, I guess in this case, positively charged hair, and so like charges repel, right? And so as a result, your hair tries to, all your hairs, I guess, try to get as far away from each other as they can. And so you're left with, well, you've seen what that looked like, right? I didn't get a picture or something like that, but kind of get the idea. And of course, this is a nice unit too for stuff like this. You can give it a try. Gets one of these materials or something like that, or get some cotton and just, if you've got any piece of clothing, rub it all over your hair and then take it away and see what happens to your hair. And if you don't have hair or a lot of hair, just do it to somebody else. Okay, another concept that's sort of important here when we're dealing with charges is the principle of superposition. You know it, you love it. The net force acting at any point in space is the sum of the individual force vectors acting at that point. And so recall, we talked about force fields before. Right? A force field is the space around an object where some force exists, and the force can vary from point to point. Usually we see it actually varies according to r squared, or the distance from the center squared, and that's going to be the same for charges as it was for gravity. So if there are multiple objects with force fields around them, the net field strength at any point in space is and I just put that vector in brackets there to emphasize that it is a vector, but it's the sum of the field strengths due to each object, right? And do remember, right, when we talked about force fields, here's just another one of the Earth. Remember, we were drawing the arrows a little bit longer as we got closer to the Earth to represent the fact that as you move closer, the field strength got stronger, right? So here, if we have two objects, this is not to scale, I think if you looked at the actual diameter of the Earth, I think the moon's somewhere around 31, 32 times that distance away. In terms of the relative sizes, though, this looks pretty good, right? It's about 27% the diameter of Earth, so it's a good sized moon for the size of our planet. But yeah, you'd have to put that a little farther away. But anyway, we'll just go with this. So we put some object, or we look at some point in space. Let's look at this point right here, right? And we want to say, like, what is the force that a particle or any mass in this case would feel or experience if it was at that point in space. And we say, well, there would be some attractive force here, right? It would be pushed in that direction. We'll call that FG of the moon. And then there would be a force. Now, it's a little farther away from the Earth, but the Earth is also a lot more massive than the moon. So it would also probably experience a force a little bit bigger. That would be of the Earth. And so as a result, right, the total force that it would experience would be the sum of these two vectors, right? So the total force would be and just to be really clear about that, we'll put some nice little vector symbols on there, right? That this would just, and you can imagine, like, if you put an object here, some mass at that point in space with two objects like that, you'd expect it roughly to go in that direction, at least initially, right? And then as it starts moving, now you've changed the positions, and so as a result, the force changes. So these, what at least at this point in space, we could look at that. And here's a fun example. With some masses, we can actually do the math. Determine the acceleration of m3 in the following gravity field. So we're told m3 is 2 times 10 to the 9 meters from each of the other two masses. So this is kind of convenient here. It's the same distance from each of these two masses. And we want to figure out, okay, what is the net force, or really we want to figure out the acceleration of m3, right, at this point in time. In order to figure out the acceleration, that means we need to figure out the force acting on it, and the force acting on it right now would just be the sum of the two forces acting on it, right? And note, in this case, there would be movement, right, for all three of them. M1 would move because of the force of M3 and M2, right? So you'd probably have something like this one moving in that direction. This one here would probably move a little bit in that direction. These are all masses, so everything attracts, right? We don't have to worry about anything repelling. And M3 we expect to sort of move somewhere in the middle like that, right? So all of them would move and clump together, but we're just interested in this initial instant in time. What is the acceleration right now because of the distances from these two masses? And they are different, right? M1 is 6 times 10 to the 10, so 60 billion kilograms, and M2 is 80 billion kilograms. So there's going to be some movement here. We can look at both of these separate, so you can say, well, what is the force, and we're interested in M3, so what is the force of mass 1 on 3? So I'll just write it as, maybe I could put a little, something like that, I don't know. And we know from gravity, we can say, well, that's just going to be G M1 M2 divided by R squared. And if we put in the numbers here, that's 6.67 times 10 to the negative 11. The two masses M1 and M2, 6 and 2. And the distance, 2 times 10 to the 9 squared. Right? So 4 times 10 to the 18 essentially at the bottom. If we do put in these numbers, and I already did, I get 2.001 you're going to love this part, times by 10 to the negative 8 newtons. So not a lot of force, right? The G is weak, right? I mean, interesting too. We're dealing with billions of kilograms, but gravity, it doesn't have much. And then we can look at the force of mass 2 on 3, or the force between the two of them. Same, in this case, M2 and M3. I'm just realizing, since the first one, I was actually looking at M1 and M3. So that means I messed up here. There's M1 and M3. Now I'm looking at 2 and 3. So I wrote that down incorrectly there. Same idea here. 6.67 times 10 to the negative 11. M2 is 8 times 10 to the 10. And M3 is still 2. And the distance between them is the same. Putting in those numbers, I get 2.668. Again, times 10 to the negative 8 newtons. So I have two forces acting on this object. I can even sort of represent these here if I want to. I can say here is the force of 3 on 2 is a little bit bigger. Or sorry, this is the force of 2 on 3, and here's the force of 1 on 3. Right? So adding these together, I'm going to expect some, just to get a different color, some vector sum of these two. This will be the force on 3, or the total force on 3 should look something like that, which would just be adding those two vectors together. And I'll put my angle this way just so I can figure out this vector. And this just means good old Pythagoras, right? The magnitude of the force on 3 is going to be the two components of this squared. So the square root of 2.001 times 10 to the negative 8 squared plus 2.668 times 10 to the negative 8 squared, which equals, if my numbers are correct, 3.334 times 10 to the negative 8 newtons. So that gives me the magnitude of that. The direction, which definitely is going to matter here. Now, if I represent theta here, I just have to be clear of which my opposite side of this triangle would be. So that would be 1 on 3, which would be this top one here, will be my numerator for the way I've drawn it. Divided by 2.668, which means theta will equal 36.9 degrees. Note also, if I'm like punching this into a calculator, the 10 to the negative 8 cancels on the top and bottom, so it's really just 2.001, and I probably could have even written it that way, just to make it clearer what exactly this is if you look at the note later. See, this is one of those nice points when you're doing a problem like this where you feel like you're done, right? And then this is why I always say go back and look at the question. I know I'm not done, but just if I look at this again, I can see here, oh yeah, it said determine the acceleration. So I'm not actually done. The acceleration of 3 is just the force on 3 divided by the mass. And so that means it's going to be oof, that was messy. Good thing it fixes it for me. 2 times 10 to the 10 was the mass. Which means the the angle is going to be exactly the same as the angle of the force, so I don't have to worry about anything there. Therefore, the acceleration of 3, if you do that quotient there, you get a very, very small number, 1.67. That's not a 1. Times by 10 to the negative 18 meters per second squared. And my direction would be, what's the 36.9, so I'll just say from M2, 36.9 degrees from M2 toward right. If you look at this angle the way I kind of drew it, I'm saying, well, here's M2, so we're kind of going from there, we're going right toward where M1 is, sorry, from M2 toward M1. So a very, very, very small number, right? That is a very small acceleration. But again, it takes a lot of mass to get, decent acceleration. Electric force, Coulomb's law. Okay. Well, let me just read it because I made this like a week ago and barely remember what I wrote. Charged particles, electrons, protons, have electric force fields around them. So basically what I'm trying to say there, I think, is if you look at gravity fields the way we just did, right, like every point in space around a massive object, or technically any mass, right, has this force field. Similarly, electric charges have these force fields around them, right? If you've got a charged particle, such as an electron or a proton, you're also going to have a force field around that. The electric force on any two particles in space is given by Coulomb's law. And you can, if you look at this equation here, right, you can see this is very, very similar to the gravitational force that we just saw, right? The only difference is instead of using the gravitational constant, we have Coulomb's constant, which we're writing as a K. And instead of the two masses, we're just multiplying by the two charges. So that's Q1 and Q2, or just whatever the charges are. And once again, we get R squared on the bottom, right? So very, very similar. But two big differences to be aware of here, right? The first here, electric force can be positive or negative. So that is definitely different than what we dealt with gravity. The other thing to be aware of, which is more conceptual if you're looking at something like this, is that K is much, much bigger than G. Right? So if you remember when we looked at G, it was, well, the 6, right? And since both are in SI units, the way they represent it, right? But you can consider like essentially 7 times 10 to the negative 11 versus 9 times 10 to the 9. Right? Big difference just in terms of value and what those are. But granted, we're representing this stuff in coulombs, so that's different than representing mass in kilograms too, right? So let's look at an example of this, just to sort of maybe appreciate the numbers. So we have an electron that's 1 meter away from a proton. So let me put my little electron here. And it's going to be 1 meter away. Let's put our proton here. Maybe that's a little far, but... All right, so 1 meter away. what mass would you need to put 1 meter away from the electron in the opposite direction so that the electron's acceleration is 0? So basically we're saying we're going to have some mass on the other side. And everything's going to be 1 meter apart, right? This here is going to be 1 meter. And this here is going to be 1 meter. Seems pretty straightforward, right? We know the electron is going to be attracted in this direction. Right? This is going to be because of the electric force, and we know it's going to be attracted in the other direction because of the gravitational force, right? Because both the electron and some mass. And for simplicity, we're just going to assume that whatever mass we need to put here, we're able to sort of concentrate it all right at that point in space, right? It is the center of mass, so it could have a little bit of space, but we'll assume this is, possible. So what would these two forces be? Well, on this side, we'll have the force of gravity. So this will be whatever that mass is. I'll just leave that as an m times by the mass of the electron. And that's all over r squared. So in this case, it's just 1 squared, which is 1. And in the opposite direction, we're going to have the electric force, which is going to be K times the charge of the electron times the charge of the proton divided by r squared, which once again is just 1 squared. Now, these two things have to be equal if the electron is not going anywhere, right? The two forces have to be the same. So since they're both over 1, or 1 squared, which is also 1, we can just say, therefore, G M M E must equal K Q E Q plus. And since M is what we actually want, we can divide both sides of this by M, E, and G, which means the mass would need to be K Q E Q divided by G M E. So I might as well put in the numbers here. That means the mass would equal to K, we said was 8.99 times 10 to the 9. The charge on a electron, well, the charge on electrons is the same as the charge on a proton. Both going to be 1.602. Was it 10 to the negative? Since this is the same, right, the charge on the proton is the same as the charge on the electron, I can just square this. G, we said before, was 6.67 times 10 to the negative 11. And the mass, I should be very clear about that. The mass of an electron, 9.11 times 10 to the negative 31, if you're writing this in kilograms. And the calculator says it is 3.7, I'll just do it as 3.8 times by 10 to the 12 kilograms. That's pretty good, right? So almost, 4 trillion kilograms. That's a lot of mass to sort of concentrate at a spot like that. But just to compare these two numbers, right? I've got on the other side of this electron, I've got one measly little proton, right? And I've got the electric charge. I'm ignoring the mass of the proton, which seems pretty reasonable given what these numbers are. On the other side of it with the electric force attracting it. So I would somehow 1 meter away on the other side have to concentrate like a mountain's worth of mass in one little tiny space like that, right? So it is just, again, there's just really no comparison And this is why we see the electric force have the effect that it does here on Earth, where gravity is comparatively like insignificant, doesn't matter at all.